calculating probabilities today. We did a fair amount yesterday about a technique, you know, the tree diagrams, the probability trees, and they're going to happen today as well. We have some other situations or other ways of calculating probabilities, and one's called Bayes' theorem, for instance. Others are called conditional probabilities. So you're going to get a whole wide variety of questions today. So here is the first one. It's like similar to question 1 homework. You're going to take 2 cards from a deck, and you're being asked to find the probability you get an 8, and then the next card is not an 8. Now, whenever you have a probability that's made up of 2 events, you're going to multiply 2 things together. You're going to multiply the probability of the first event times the second event. Now, if you imagine the first event is you get an 8. There are 4 of them in a deck of 52, 4 out of 52. Agreed? Now, in this story, the way it was described is you've got the deck of cards, right? You turn it over and it's an 8, and then you turn the next one over and it's not an 8. So the second one, this one here, is going to be a little bit different from that one. For starters, since this one was an 8, isn't there only 51 cards left? How many of those 51 cards are not an 8? And you've got to assume that this has already happened. So you've got an 8, and this is a probability. The 8 has happened. So how many are not 8s for the second one?
48.
And those 2 multiplied together are going to give you the answer, and they want it rounded off, I believe, to 3 decimal places. So I like to play safe when there's lots of fractions going around, so I'll put a little bracket. That's me playing safe. There's 450 seconds times. If you're wondering where that 48 came from, if you think of all the cards that are left that aren't 8s, there's 12 of those cards times 4 suits. So that's where the 48 came from. And so we get about 0.724. And that's our first probability. Now, next guy is going to use a thing called Bayes' theorem. Bayes' theorem is a way to calculate conditional probabilities, right? The probability of something happening given something else has happened, right? So the probability of A given B. And Bayes' theorem says, this is one of its many versions, that the probability of A given B is the probability of both happening divided by the probability of B. And this bit up here is, look, don't try and do this if one or both the probabilities are 0, because dividing by 0 is a bad idea. Now you can have it this way around, or you could have it that way around, right? Depends on who you want to call A and who you want to call B. So this one is similar to question 2 on the homework. In this story, they talk about a cafe owner, and he knows that 95% of the people who he serves drink coffee. So it's probably a coffee shop. And the number of people who also order a biscotti. So they do, I want a coffee and a biscotti. I think it's one of those really ugly hard biscuit things. I don't drink coffee, so I think that's what it is. And 20%, 0.2% of his patronage does this. And they then go on and ask you things like, what is the probability that they order a biscotti given that they have coffee? So according to Bayes' theorem, that's the probability of A and B, right, of both things happening, divided by the probability of A. Well, if you look at this question, all the numbers you need are here. There's both and there on the bottom is that one. So I just go and I do 0.2 divided by 0.95, and the answer I get is 0.211, I believe. And then they ask, what's the probability that they don't order a biscotti, given that they had a coffee? Well, if you look at this one, that's the thing happening. And this is the same thing, but it not happening. So we would say, well, I would look at that and I'd say, well, that's the complement of that, right? You're either doing it or you're not doing it, right? In this world. And so that ends up being 0.789. I basically just took that away. So we're into the realm now where probabilities are getting a little bit more complex, right? A little bit different ways that you have to figure out how you're going to calculate them. So that's two examples, one with the Bayes theorem, and the other was multiplication of two events where one event had an effect on the other. Okay, that's just two questions. That's maybe a good point for me to say, do we have any questions? You comfortable with those two? Okay, just try to work my way through then. The next one in our list, let's show you that one rather than me trying to read it. Here we go. In this next question, we have a table. And this was a survey of 123 families. So I can assume that this adds up to 123. And it's families that have two children. And in each of these boxes, they put what the first child was and what the second child was. So for instance, that 37 would be a family where the first child was a male and the second was also a male. This 27 would be the first child was a female, but the second one was a male. Right? And from this table, again, they're all about different situations, different ways of giving you information that you've then to suck out probabilities from. From this table, what is the probability that you randomly select one member of the family, and let's read this carefully, did not have two children who were both male? God, that's like double negatives, isn't it? Right, so they did not have two children who were both male. Okay, so if you find out the ones that were both male, it's that one, agreed? But aren't they talking about, in a very weird way of saying it, the other three numbers? Does that make sense? It's not that, right? It's not the 37, it's the other. So if I say 24, 27, and 35, I'm not going to risk that. So I go 24, add 27, add 35, I get 86. So that's 86 divided by 123. And I get, what do they want here? 2 decimal places. Well, when I rounded it off, I get that. So are you comfortable that they're talking about these two and that one? And that's where the 86 came from, divided by the total number. There is a different way to come up with that same answer, isn't there? Couldn't I have tackled it from the problem of, okay, let's find out what that number is. Now, if I go in my calculator and I find out what 37 out of 123 is, the answer is 0.30. So couldn't I have made this one takeaway 0.3 and come up with the 0.7? I could have done the complement. If that table was really big, right, like it had 8 rows and 5 things in each row, wouldn't it have been a lot easier just to find the one number and take it away from that single probability and take it away from 1 than to add up all the other numbers in that huge, big, ugly table. Right? So the strategy is that sometimes it's easier to find the thing you're not looking for, 0.3, and subtract it from 1. Oh, here's a little jargon word I haven't used for a while. Is this particular fraction a statistic? It happens to come from both being female. Is that called a statistic, that particular number?
Yes.
Yes. If the thing wasn't a survey, which it is, right, then it wouldn't be called a statistic. Wouldn't be called a parameter. Right? If they did everybody in the world, it would be a population you'd be getting your data from. That's what that fella looks like. And there's our answers. What those answers, they distract me. Stop doing that. Are you comfortable with that one? Right. So now going to move back to our kind of written stuff. And we'll look at our next question. This is a version of question 4. A woman plans to have 2 children. The probability of getting a boy is 0.533. And they then go on and they talk about the 2 children that she's going to have are independent. In other words, if the first one's a boy, the chance that the second one's a boy is still going to be that number. In the jargon of probability, we would say that was a with replacement situation, right? And we're being asked to find what's the probability that she will have 1 child of each sex, right? So although you only told me the boy, how come I know that's the probability of a girl? They never told me, but how do I know that that must be?
Because if it's if the boy is that percent, if the boy is that decimal, then the girl has to be the other portion of the 1.
Yeah. So basically, right, that calculation. So I'm going to create one of these trees. And I'm going to put boy and girl. And then our second child could be a boy or a girl. Boy or a girl. In this particular one, we're trying to find the probability that she gets 1 of each. It's just another way of saying a boy and a girl, right? So on this branch, we put the probability of a boy. And on this branch, we put the probability in a girl. Since these are not affected by what happened in the past, these numbers stay exactly the same. So a boy is still going to be 0.533 and a girl is going to be 0.467. Remember those trees from yesterday, right? Now, I don't need to complete the ends for everybody because I want to save time. And since I'm only looking for 1 of each, would you agree that this event here was a boy, then a girl, and then this event here, a girl, then a boy? Aren't they the only 2 that I need to worry about? And that's the 2 I'm going to calculate. And then if I add them together, bingo, right? We've got the answer. Now, to get this probability, which is a boy first and then a girl second, you would multiply the paths, the roads together. So it's a 0.533 by a 0.467. And they want these answers to 4 decimal places, so that's what I'm going to do. So 0.533 times 0.467, I'm looking at what many decimals? I wanted 4. 2489. Be comfortable with that? Now, again, I want to save some time. If I do the second one, which is a girl first and then a boy, would you agree it's going to end up being the same number because it's the same two numbers multiplied, just the order was switched. So I can put in another 0.2489. You comfortable with that? Just to save time. Now, we want this event. I could, and I'm writing it down, so that means it's possible to do that. Can I just add them together? Or I could just double them. Wouldn't it be the same effect? And so if we do that, we get 8 carry 1, 17 carry 1, 9. It's almost 50% of the time, isn't it? It's about 49.78%, which seems reasonable, right? You get a boy and a girl. It's going to happen about half the time. You get one of each. Okay, so that was an example of a question where the tree diagram, probability tree, was helpful. Remember the one about the biscuits and coffee? That was using this formula called Bayes' theorem. And in this question, didn't we just multiply two things together, noticing that one affected the other? So we've kind of seen three different situations that required slightly different ways to solve them.
I have a question.
Yes.
So if the two events are the same event, like two boys being born, you add them together instead of multiplying?
If the event had been, what's the probability that you get a boy and then another boy? You would only have one pathway, this pathway here. That would be the only one that you would calculate. And that would be this times this, which would be about 0.25, 0.26. Now, if you wanted to know what's the probability that you got two girls, wouldn't it only be one pathway, this one here? So,
Okay.
So if it was two boys, you would multiply the 0.533 times the 0.533.
Okay, because I just noticed that down there you had added two things together.
Yeah, I added essentially this event and this event because these were the two different ways in which you could get a boy and a girl.
Okay, I got it.
Okay. Show you one where you don't need a tree diagram. Let's say the probability that it rains, do that one again, is 0.7. So we're in this place, it's really raining. So that means that the probability that it doesn't rain, which I'm going to just call dry, is 0.3, right? So that's information you're given. I can find the probability that it rains. Seven days in a row. Now, the chances that it rains on any given day is about 70%. So that's a place that rains a lot, right? But we're being asked 7 days in a row. We make the assumption here that if it rains on one particular day, it has no effect in the others. So if I wanted to do this, I could find the probability that it rains times the probability it rains, and I'm too lazy to write them all down, times the probability that it rains. Would that make sense? You can just multiply probabilities together, and in a situation where one event has no effect on the next, you can simply keep the number the same. And so you could go 0.7 times 0.7, right? And you could do it 7 times. In mathematics, we have a little guy that looks like that. Isn't that the short way of saying 0.7? And that makes it easier. I'm about to do that calculation. Do you think it's going to be less than 50% of the time, less than 10% of the time, or less than 1% of the time? Less than. What's your gut feeling?
Say less than 1% even.
Okay, let's find out. It's about 8% of the time. So it's less than 10% of the time. So even if you lived in a really, really rainy place, isn't it still very unlikely you'll get a whole week of rain? Now, will it harm? Yeah, it'll probably harm about 8% of the time. And if this is the place you're going on holiday, it's probably going to be that's the 1 week of the year, right, where it harms, right? That's called Murphy's Law. That is not a law that we've been able to prove, but my expectations have told us that. Since I'm homesick and I'm trying to get home every time and COVID stops me, I've been home lots of times before COVID, and I typically go in August when the summer classes finish. And Scotland's a gorgeous place, beautiful place. I love it to death, but don't go for the weather. Scottish weather is very like here. It's just colder, right? A lot of rain, but it's cold. And I've visited back home for about 2 weeks, and sometimes I've went and it's been 2 weeks and it maybe rained one day. It was great. And I remember 1 year, about 10 years ago, I went there and I was there for 14 days and it rained for 12 of them. So the randomness in Scottish weather. You could go and have, that great fortnight that I had, right? 2 weeks, gorgeous weather. You could go the next year and be lucky to see, be dry for 2 days. Well, there's our probabilities. Now, our next story is going to be similar to question 5. And here there's a raffle. And I'm just reading this straight out. A raffle is held in a club in which 12 of the 35 members who bought raffle tickets are good friends. So the probability that they are friends is 12 out of 35. Okay. All right, so these are friends of the president. Well, that matters, but anyway. So that's what we need. Now, the president draws 2 winners. Round your answer to 4 decimal places. Now, the first one talks about the 2 winners are drawn with replacement. Now, what that means is they pick somebody and say, hey, George, you've won the bottle of whiskey, right? I picked your raffle ticket out, you've won the bottle of whiskey. John says, oh, great, and he goes back and he sits down and they pull out another number and they could pick George again, right? He's allowed to win. You ever been to a raffle where somebody ends up winning twice, and everybody else thinks it's been rigged? Well, maybe this is what they think's going on here. So 2 people, right, are going to be chosen, drawn with replacement. What's the probability that you get a friend of the president and a friend of the president, right? Now, I could do this question using a tree diagram, right? It'd be friend, not a friend, friend, not a friend, friend, not a friend, and it would work that way. But since it's with replacement, can't I just multiply them together like this? Now, what's the chance that you're a friend? 12 out of 35. That's the chance that you pick somebody who's his friend. What about the next time? It's still 12 out of 35 because the same guy who won could be in the pack that wins the second time. Are you comfortable with how the probability of 2 things, you just multiply them together, and if the 2 things don't change, then it's the same fraction each time? And then you go to your calculator and you put your little brackets around and you go 12 divided by 35, and then you go times 12 divided by 35, and what are they looking for? 4 decimal places, so 0.1176. Now, the second situation is going to be without replacement. Now, that would mean If George gets picked the first time and gets a bottle of whiskey, he ain't going to win again, right? So we can still calculate the probability that two friends were chosen. The first friend is going to be 12 out of 35, agreed? Now, that person, that friend, is now used up. That means the next one, the next person chosen, also being a friend, is not the same as the original, because there has been a change, right? Since one person has been used up, won't there only be 34 people who could win? And how many of that 34 that are left are friends?
11.
Do you see in this second case, only the second probability changes? Now, you multiply those two together and you've got your answer. And this time, the answer is 0.1109. Now, they're very similar, which you'd expect, but they're still different, right? You can tell that they're not the same probabilities, right? This is a little bit less chance of happening, which kind of makes sense that you're using up something. It gets a little bit less likely. Oh, this one is a little bit trickier. In question C, it's going to be, let's check it, is with replacement again. And they want to know what's the probability that it's not a friend and not a friend. So somebody who's not a friend of the president and the next one is. Now, since it's with replacement, you can calculate it doing this, right? And since it's with replacement, the numbers go back in. Right, if you know that this is a friend, can't you find the probability that someone is not their friend? Right, 12 out of 35 is the probability that you're a friend, right? 12 out of 35 of them. So won't the not friends be the rest? Well, if you take 12 away from that, I believe you get 23. Are you comfortable where I got the not friend probability from? Right, out of 35, 12 are, 23 are not. So this guy is going to be 23 out of 35. Since it's with replacement, what's the probability that the second person is not a friend as well? What's this fraction?
22 out of 35 again?
Yeah. When you see with replacement, the probabilities don't change, right? It's the same thing each time. So if you wanted to pick three people, it would be this guy times this guy times this guy again. Now, the last one is without replacement. And they want to see this probability. So the probability that it's not a friend in both cases would be, well, 23 out of 35, that's the first one. But just like over here, isn't this second situation going to change a little bit? Because that first person has been used up. So he's not a friend, right? That's used up. Doesn't that mean you've only 22 people who are not a friend? And there's 34 people to do it with. Now you multiply those to get this answer, you multiply those to get this answer. Do you see the difference to a probability of two events happening? With replacement, the numbers don't change, right? They're the same number forever. Without replacement, they do change. So a similar situation I'm going to do with cards. If you pick only one card, the probability that you get an ace is 4 out of 52. Agreed? 4 aces out of a deck. Let's do what typically happens with cards. Let's do without replacement. Isn't that really what happens? You shuffle a card, you turn it over, you turn it over, you turn it over. We are going to do 3 cards in a row. So you've been dealt 3 cards. And what's the probability every single one of them is an ace? Well, the first one being an ace is 4 out of 52, right? It's that guy. What's going to be the next probability? Remember, this has happened now. So you've already got an ace. What's the probability that the second one's going to be an ace? Top
3,
number.
1.
3, right? 3 aces left out of the 51 cards in the deck. What's the probability now that the third one is also going to be an ace, given that these 2 things, you know, have happened?
2 out of 50.
Do you see there's a kind of pattern here? If I went and did 4 aces, wouldn't the next one be 1 out of 49, right? Now, if you've ever played card games and somebody dealt you 3 aces, wouldn't you consider yourself very lucky? Let's see how unlikely that number is, because it should be quite tiny. So 4 divided by 52 multiplied by 3 divided by 51. Did I multiply that? I did, good. Times 2 and divided by 50. Do you see that funny little e negative 1 that's there? Or e negative 4? What we've got is a number that looks something like this, 1.8 roughly, e to the negative 4. That is scientific notation. Hopefully you've done a science class. It's that guy. That's how the calculator does 10 to the negative 4. If you don't know what that looks like because you're not aware of scientific notation, an easy way of saying that is how many zeros you start with. If it's negative 4, including this 0, you start with 4 zeros. Is it not a tiny probability? Now, if I multiply that number by 100, it's about 0.018%. It's about 1 in 50,000. You'd have to play 50,000 games where you're dealt 3 cards, right? 50,000 to be dealt 3 aces. Right. So if you ever see the movies where the guy gets dealt 3 aces, shouldn't you be highly suspicious about the reality of it? Unless the movie was about somebody cheating, right? Also, if you ever play a gambling game and aces are good, shouldn't you bet all your money if you get 3 aces, right? It's such an unusual event, right? It'd be hard to be beaten. Okay. Any questions? Are we good? Okay. Let's do some more. So version of question 6. Suppose there's a school that only has 11 and 12th grades. And half of them are in each grade. And these students are called seniors and juniors. So there's going to be a lot of information to deal with there. Seniors and juniors, right? And half of the seniors take calculus, and 70% of the juniors take calculus. And we are asked to create a hypothetical table of 100 students. And the table is going to look something like this. You're going to have the juniors, the seniors, those who take calculus and those who don't take calculus. And we're meant to find what numbers go here if there was 100 students in total. So there's a lot going on here. We're told that it's 11 and 12, so that's basically junior and seniors, right? And we're told that half of the seniors take calculus and 70% of the juniors take calculus. And somehow we are going to have to figure out what numbers, like, is it 22 in this place and 14 here and 17 there? Now, when you give me information that is in this form, to me, the simplest way is to do a probability tree. And I'm going to start with senior and junior. So that would be the first split. Now, since they told me it's half and half, I'm going to turn them into decimals because they're just easier to work with. So far, so good. Now, the second thing you told me was to do with calculus. Half the seniors take calculus. So I'll call this one calc, means you take calculus, and that's 0.5. But there's also another possibility, and that's going to be the ones that don't take calculus, right? And then for the juniors, we have two possible events. They take calculus, which is 0.7, or they don't take calculus. Now, there's two numbers missing from my tree. The one that goes here, right, it's a decimal, and the one that goes here. And I need those, because once I get those, I'll be able to help fill this table in. You know that 0.5 of seniors take calculus. So what fraction or decimal don't take calculus? Don't overthink.
0.5.
Right. Don't those two things have to add up to 1? Because you can either do 1 or not. Now, if you do 0.7 who take calculus, would you agree then that makes 0.3 they don't take calculus group? Now, whenever you create one of these tables, don't we then finish by the probabilities of the 4 endpoints? Now, if you take this one, it's 0.5 times 0.5, which ends up being 0.25. And if you take this one, it ends up being also 0.5 times 0.5, which is 0.25. If you do 0.5 junior times 0.7, you get 0.35. And then if you do 0.5 times 0.3, the last one on the list, you get 0.15. If I did this correctly, what should those 4 answers add up to every single time? What should they should add up to 1. So if you're doing one of these complicated tree diagrams, one way to check your answer is just to add up these 4 guys. Now you might say, well, okay, you've got these, but what they want over here isn't, you know, the decimals that would go in each of these 4, because each one of these actually corresponds to one of these, right? But we could get it. Let's take an example. A junior who takes calculus, right? If I look at a junior who takes calculus, is it not 0.35? Now, 0.35 of 100 is simply 35. Do you see where it came from? And if I wanted to do these ones, these are juniors who don't take calculus. And if you do juniors who don't take calculus, it's about what, 15% of them, right? 0.15, which ends up being 1.5. And this ends up being 2.5, and this ends up being 2.5. Now, I wish they'd made this number awkward, you know, like 400. Because then wouldn't you be doing 400 times this, 400 times this, and this, and this, and there's your answers. How we go? There's another question like this, but the number is, I think, 100,000 or 10,000. So that I kind of like because it was big. So far, so good. Now, question 7 is very like 6, so I'll skip it. And let me show you question 8. Good grief, didn't realize how much time we've gone by. Right. Do you see it's basically, what the heck is happening? Do you see that this is a tree diagram? Right, it's probably got more writing than I would typically do it. But in this story, an airline offers a thing called advanced purchase fares. So like if you buy a ticket, 6 months ahead, you get a better deal than if you buy a ticket with 2 days to go. I think if any of you've ever had to get, like, I have to get to Kansas tomorrow, aren't you going to pay a lot more money than if you booked it 6 months ahead, right? Pretty common airlines to do that. And in their case, you only need to be 4 weeks, which is quite nice of them. The airline has noticed that 70% of its customers who buy tickets don't take advantage of the advanced purchase fares. In other words, they buy a ticket, relatively in a short time interval, right? But the other 30% do, which makes sense. The no-show rate is the second event. The no-show rate for those who don't get one of these purchases is 20%. And you might think that's weird that people buy airline tickets and don't turn up, but actually that's not as uncommon as you would think. Does anybody know why people don't turn up, even though they've bought a ticket? Some of them are businessmen that just cancel the meeting. I'll just talk to the guy on the phone, or I'll send an email. Do you know if you don't pay for it, you don't tend to care if you cancel a flight? Would you agree? Hey, it's not my money, right? So businesses are notoriously bad at that. Hey, you might have to go down there tomorrow or next week. We'll get you a ticket. Oh, it's okay. It sorted itself out. The fire's out. You don't need to go down there. Yeah, ticket doesn't get used. This whole packet information is going to be put into this probability tree, and we'll be finding all the numbers for A, B, C, D. This is how WebAssign does one of the tree diagrams, right? It gives you the picture, and then you're going to be putting in each of the probabilities that go here, here, and here. And that's the guy I'm going to try and get done in the short time that we've got. So here it goes. The first split was people who do advanced tickets and those who don't do advanced tickets. And we are told, let me read it, that 70% don't use that form of ticket, so the other 30 does, right? So we're told that. That's where that goes, right? 70% of people don't get an advanced ticket, 30% do. Now, what happens next is that they show up or they don't. So we'll call these no-shows. Right, that's people who don't, and then show up. And then there's going to be a no-show. And then they're going to show up. That's basically a copy of the picture. Now let's see what we have in the storyline. If I read a little bit further on, the no-show rate for those who don't buy an advance purchase, the no-show rate for those people is 20%. Okay, 20% don't show up. How many do show up? They don't tell me it, but I should be able to calculate.
.8.
Have you noticed that the two branches always add up to 1? Because you either do this or you do that. You either show up or you don't. So the two branches add up to 1. Doesn't that mean you only really need to tell me one of the two and I can figure out who the other one has to be? So in the last one, it's a 10% who don't show up. And that makes 90% who do show up. So far, so good. Now, at the end, don't we have to multiply these guys to get the last probabilities? Now, for instance, this one times this one is going to happen 0.14 of the time. This one times this one is going to happen 0.56 at the time. This one times this one is only going to be that number. And this one times this one is that number. Okay, just trust me that I do them in my head and I did them right. And what you would have there is a list of things that would look like this. A, B, I think one of them at the end is called U. A is 0.7 because it's got a lolly on it. B is 0.3. This guy at the end is called U, and so U ends up being 0.27. Do you see how now you can create that table and put it into WebAssign? That's how WebAssign does probability trees. Are we good with that? And we have reached the end for today. Perfect timing. So make sure you've got your last name down as attendance. And I will see you tomorrow. And I'll hang about for anybody who has questions. Carson, do you have a question for me? No? Okay then, I will see you tomorrow.